Welcome to Engineering Illustrated. Today we've got an eye bolt and ceiling with two ropes pulling in different directions. Our goal is to combine the forces into one resultant force to figure out what the eye bolt is feeling. This example will demonstrate two helpful techniques. First, how to resolve a force vector into its Cartesian components, and second, how to combine several Cartesian components into a single resultant vector. Then we'll find its magnitude and direction. First, let's read the problem statement to make sure we're looking for the right thing. Determine the resultant force, F sub r, and its direction measured from the x-axis. It's important to establish the positive directions before getting into the problem and confusing things. The positive directions will be right and up for this problem. By sticking to this convention, we won't have to worry when to add or subtract components because the negatives will take care of themselves. All we have to do is just add everything up. Before doing any calculations, it's always a good idea to simplify the problem by making a free body diagram, or FBD. Let's reduce the eye bolt to a point and remove everything but the applied forces. Now let's get on to solving the problem. The most intuitive way that I find to do this is by breaking each force vector into its individual x and y components. Let's focus on the one on the right and call it F1. F1 has a magnitude of 300 newtons and acts 45 degrees clockwise from the positive x-axis. This means F1 acts in the positive x direction and the negative y direction. It's important to add those signs to the components in order to maintain the positive convention. The x and y components of F1 can be arranged to make up the sides of a right triangle with F1 forming the hypotenuse. This is called the triangle rule for vectors. Using simple trigonometry, we can find the length of F1x and F1y. The y component can be expressed as F1y equals the sine of 45 times negative 300. And the x component can be expressed as F1x equals the cosine of 45 times 300. As a note, cosine gives x and sine gives y is usually true, but it's always a good idea to verify that you're using the right trig function by remembering SOHCAHTOA. Now, combining our components, we find that F1 can be written in Cartesian form as 212.1i minus 212.1j, which makes sense because it's a 45-degree angle that goes to the right and down. Once we've resolved F1 into its Cartesian components, the original vector is essentially absorbed and not used in further calculations. Resolving the other vector, we'll call F2, is the same process, so we'll do it quicker. F2 has a magnitude of 500 newtons and is directed 30 degrees counterclockwise from the negative x-axis, giving us negative components for both x and y. Using the same technique, we find that F2x equals negative 433 newtons and F2y equals negative 250. Again, remember SOHCAHTOA to verify we use the right trig functions. Now that we have everything in Cartesian form, we simply add like terms to get our resultant vector's Cartesian components. Summing the x components gives us negative 220.9 newtons in the I direction. Similarly, adding the y components gives us negative 462.1 newtons in the j direction. Putting those two together gives us the force resultant, negative 220.9 I minus 462.1 j. From these Cartesian components, we need to find the magnitude and direction of the resultant force in order to answer the question. To find the magnitude, we again use the triangle. The x and y components are arranged to form the sides of a right triangle, with the resultant vector forming the hypotenuse. The length of the hypotenuse is the magnitude of the resultant force, which is what the problem is asking for. The classic Pythagorean theorem can help us find it. A squared plus b squared equals c squared can be solved for c as shown below. Plugging in our values, we find the magnitude of the force resultant is 512.2 newtons. Now that we have the magnitude, we need a direction in order to fully define the resultant vector. We'll need some more trig for that. This time we'll use a tangent. Looking at our resultant triangle, remember that tangent of theta equals opposite over adjacent. In our case, opposite and adjacent are FRY and FRX, respectively. If we solve for theta and plug it into our calculator, we get that theta equals 64.5 degrees, which gives us our final answer. The resultant force vector has a magnitude of 512.2 newtons and is oriented 64.5 degrees from the x-axis. This process can be directly applied to problems containing any number of 2D vectors. First, establish the coordinate system, then draw a free body diagram. Break each vector into its components. Add up the x components, then the y components, and use trig to put the answer in the form the problem is asking for. It's always worth double checking to make sure you answered the right question. Thanks for watching, and I hope this was helpful. My goal is to create concise, easy to understand content based around undergraduate engineering courses. Let me know in the comments what content you would like to see explained visually and leave suggestions on how I can improve. And I'll see you next time.